Institute of Mathematics, Police Academy of Sciences, and Institute of Mathematics, University of Wroclaw. And the title of his talk is Dimension-Free LP Estimates for Maximal Ridge Transform. So the thing with this, I would like to invite him to deliver his talk, and I also request all the participants to mute their microphones. So over to you, Wrobel. Okay.
I'm ready. Okay. Thank you very much. Okay. Thank you very much for giving me this opportunity to present this topic at your seminar. So I will speak about this dimension-free LP estimates for maximal Riesz transforms, and the point will be that we would like to obtain those kinds of bounds by somewhat using some previous results for non-maximal Riesz transforms. And the talk is based on joint work with Maciej Kucharski, my student, and Jacek Zienkiewicz. So before going into the details, I need to introduce the notation. So we'll always work on the space RD, and LP will always mean LP of RD, and the little p will be the LP norm. K will be a fixed non-negative integer, which will just mean the order of the space of spherical, the degree, sorry, of the space of spherical harmonics on degree K on RD. And the spherical harmonics are just homogeneous of order K harmonic polynomials on RD. Okay, so for P in this space of spherical harmonics, we define the kernel of the Riesz transform, Kp, and gamma k is a particular constant. It is important for the results to keep the constants, to remember what the constants are, but it's not important, not important for this talk, so you don't need to remember what that is. So in the definition, we have p in the numerator and a power x to k plus d in the denominator, and p is in hk, which means that it's harmonic. Okay, so when k is equal to 1, then what I'm writing above is just the kernel kxj of the classical first order Riesz transform, which I will abbreviate rxj or rj. All right, so the definitions of the Riesz transforms that we have are based on this Kp kernel that we had above. So Kp is here. The truncated Riesz transform is just the integral against K, the convolution with the Kp kernel when it's truncated over the level y greater than t. Then we can consider just the Riesz transform, which is the limit of which can be defined as the limit of the truncations. And finally, we can also consider the maximal Riesz transform, which is the supremum over all of the truncations. Of course, if we look at those definitions, then the maximal Riesz transform is larger than just the Riesz transform. So if you prove some bounds for the maximal Riesz transform, you immediately obtain those bounds for the...
Okay, so sorry to disturb, a little bit of echo is coming from background. It is from your background or some participant's background? Little bit of echo.
I also see the echo, hear the echo, but I think it's not from mine. I'm not sure. So
just is the...
Okay, is it better now?
Okay.
I think it's better, right?
Okay. Yeah.
Yeah, somebody's microphone. Okay, thank you. Okay, so yeah, so these are the three objects that we will consider, and we'll be mostly interested in this one, the RP star, which is here. Okay, so there is a classical result of Stein from the 80s, which says that if you take the vector of just the Riesz transforms, sorry, you take the vector of the Riesz transforms, make a square function out of this vector like here, compute the LP norm of this square function, then what Stein proved in the 80s is that this object is controlled in a dimension-free fashion in terms of the LP norm of F, where crucially, this constant C of P here is independent of D. So if you use Calderon-Zygmunt theory, you get some constant, but one can prove that the constant for this vector is actually independent of the dimension. Just a side remark, why should we care maybe about such estimates? Well, direct consequences of those are some estimates for the gradient. For example, the LP norm of the gradient is controlled by the square root of the Laplacian with a constant that is independent of D. And a similar thing can be directly deduced from this estimate of Stein for the matrix of the partial derivatives, that it is controlled just by the Laplacian with a constant that is independent of D. So such things may appear sometimes in PDEs. So this is why these constants may be useful, knowing an estimate for them. Okay, and what are our goals? So our goals is to prove similar result to Stein with Rxj being replaced by its maximal counterpart. So remember that Rxj is just the Riesz transform, Rxj star is the maximal truncated Riesz transform, which means we take the maximum over all of the truncations. And we would like to prove a similar estimate as, say, for example, we would like to prove a similar estimate as Stein with star being put here, whereas in Stein's theorem, there was no star here, there were just Riesz transforms. So obviously what we are trying to achieve is harder than what follows from Stein's result. Okay, another goal that we would like to set for this lecture and for this paper that we have written was to control somehow the Riesz transform, the maximal Riesz transform RP star, in terms just of the Riesz transform RP. I mean, of course, such a control is probably impossible pointwise, but we would like an LP control of the norms. Additionally, we would like this control to be in a dimension-free way, meaning that the constant from passing from here to here is independent of D. Okay, but the dependence on K, the degree of P is allowed in what we are considering. Also, as a side of our estimates, we will have explicit dependence on P. I will write it in a moment later, but for the purpose of this talk, you can forget about the dependence on P and on K as well. It's just important that we realize that what we are achieving is independent of the dimension. So for the purpose of this talk, let's say that we just care about the dependence of the dimension. Dependence on P and dependence on K is irrelevant. All right, so let me first state some previous result in this line of research. So when K is equal to 1, there is a paper of Mateu and Verdera from 2006, where they proved that among other things, they proved that the maximal Riesz transform here is controlled by the Riesz transform in terms of their LP norms at the price of a constant which depends on P and D, and what their method gives is something of the order 4 to the D or 2 to the D, something exponential in D. A warning here is maybe in order. So essentially any method that will use doubling properties of the balls in RD will produce an exponential constant. So this means we sort of need to stay away from those methods that use doubling properties of the balls. For example, Calderon-Zygmunt theory has this feature, and that therefore is not so maybe useful in the kinds of problems that we consider. Another result that has been proved 3 years ago with my student Maciej is that if you take K equal to 1, so just the classical first order Riesz transform, and P equal to 2, so we are after an L2 estimate, then you can prove this kind of bound with an explicit constant which we computed there. Okay, so what about general odd indices K? I mentioned so far just K equal to 1. So when K is a general odd index and P is a spherical harmonic in the space HK, then one can prove similar estimates, again with a constant C of PKD, which grows exponentially in the dimension. And this follows from a paper of Mateu, Wrobel, Perez, and Verdera from 2010. Similarly, for general even K, when we take a general spherical harmonic of degree K, then you can prove an analogous estimate, again with a constant C of PKD, which grows exponentially with the dimension. So I should mention perhaps that these results of Mateu, Wrobel, Perez, Verdera generalize to broader classes of singular integral operators with odd kernels and with even kernels. And these were the topics of their paper, but among them one can deduce also these results that I mentioned here. Okay, so what are our results? What I would like to describe and to maybe give some ideas about the proofs. So first of all, for single Riesz transforms, we have an estimate for RP star in terms of RPF for all degrees K, all P between 1 and infinity, where estimate is of this form that crucially it is independent of the dimension, and there is some dependence on P, which is explicit, and on K, which is not explicit. But as I mentioned, for this talk, let's just focus on the thing that the estimate is independent of the dimension D. Okay, so another theorem that we have is the one that we have for vectors of Riesz transforms. It means that you can, instead of just taking one Riesz transform, you can take any subset of the spherical harmonics of degree K. You make a full square function out of this subset, and then this is controlled in terms of some constant that does not depend on D by the full square function without the stars here. So this is just a Riesz transform here, but it doesn't have a star in this place. So this is the Riesz transform, but not the maximal Riesz transform. And one can continue because for this object, the vector of Riesz transforms without the star is controlled just by the function. So one can also finish with something like this times a constant that depends on P. Okay, so this results. Yes.
Here, can I ask something here?
Yeah, sure, sure.
Here, GK is a subset of K, so it allowed to be countable, right? Not just finite.
No, HK, right, but then, okay, so let's say it's finite, but then in some cases this estimate may mean nothing because on the right we are still summing over the same subset. So if it's too, for example, let's say that it's very large, then maybe it doesn't make sense. So when it really makes sense, what kind of subsets make sense here are some subsets of either a basis of HK or some linearly independent subset of HK. Those are those that really are meaningful in this statement, although the statement is true for any subset, but the ones that you would like to apply are of this kind.
Okay.
A basis. Thanks. Let's say we are thinking about the basis or the full basis of HK or some sublinear, sorry, independent subsystem.
Okay, thanks.
You're welcome. Okay, so as I mentioned, this C of K is the independent of D. That's the crucial thing here. Okay, and we can continue with the estimate for the LP norm of F. So in particular, I mentioned this because it recovers what I set as one of the initial goals, that if you take the stars over the Riesz transforms here, then you can prove an analog of Stein result, and this theorem implies that you can indeed prove such an analog. Okay, so now I will try to describe some steps in the proofs. Well, at least I will overview all of the steps in the proofs and maybe give some rough sketch of how these steps are performed. So let's first focus on the case K equal 1. What would be the possible approaches? So one approach when you want to compare maximal singular integrals with singular integrals is to use Kotlar's inequality. And this inequality is written here. It says for the Riesz transform of the first order, it says that the Riesz transform is controlled by the maximal function of F, the maximal function of the Riesz transform, times a constant which comes from the method. With this approach, there are two problems that essentially say that it's not the suitable one for our problem. First of all, the constant C of D depends on D, because in the proof you use the doubling properties of the ball at some point. And another problem is that we were really trying to in a way estimate R star only in terms of R. So we have R star here and R here, and we don't want the extra term, the M maximal function on F, because it does not depend on the Riesz transform. So the second term for the purpose of what we are trying to prove, this is also problematic, that you have just the Hardy-Littlewood maximal function on the right. Another approach would be, yes?
Can you repeat that thing once more when you said that after that you said that it uses doubling property? So you want to avoid this thing?
Yeah, exactly. Right. So I don't remember exactly how the proof went there, but I'm sure that the constant it produces is exponential. So the problem maybe, okay, the doubling property is usually the way where you get exponential constant, because the measure of double ball is 2 to the D, the measure of ball. But if there is any other step in the proof which gives an exponential constant, that it's also not applicable to what we are trying to prove. Let me put it this way. So
okay,
sorry?
What is the problem with the Hardy-Littlewood method?
Okay. The problem is with the second term. Okay. The problem is that we want to have some object, let's say, I don't know, T, that depends on the Riesz transform. And this one does not depend on the Riesz transform. It just depends on the function F. Because one of the goals was that we wanted to estimate the maximal Riesz transform in terms of the Riesz transform. And if you write the Hardy-Littlewood maximal function here, you don't see the Riesz transform anymore. So for this goal, this is bad to have it there. And funnily enough, even for the second goal, we don't know, like the second goal was, or the first goal, say, was just to estimate the square function like in Stein in terms of the function. So that was our first goal, let's say. Something of this sort. Okay, but funnily enough, even if I'm just focusing on the first goal, we still don't know how to prove it without doing the second goal in a way. because the proofs that we have work in this way. So even for the first goal, it's sort of not good to have the Riesz transform here. For the second goal, which meant that we wanted to estimate this object in terms of something of the other object, this is for sure bad, but also I'm saying that for the first goal is also maybe not good because we don't know how to do it differently. So this is why we are not happy about the hardly iterative Riesz transform there. Does this answer your question to some degree, at least?
Yes.
Okay, so second approach would be to use the method of rotations, similarly to say how they are doing it in Duandi, Coatocea, and Rubio de Francia. So what happens if you apply this method? You can express the truncated Riesz transform in terms of an average of directional Hilbert transforms in this manner. The average is taken over spheres. This d omega is the normalized spherical measure. The square root of d that is appearing here it gets eaten in the estimate, so don't worry about it, that it is there. And this method is okay. It works for proving this estimate. And that's it. How much you can get from that. And this estimate, of course, does not imply the one that I copied here. So this method is okay, but there are two problems with it. First, that it does not imply this that we wanted, and second of all, that if we are about the second goal of controlling the maximal Riesz transform in terms of the Riesz transform, then again we lost the Riesz transform on the right, because here it just depends on f, and there is no say rxjf on the right. Okay, so these two approaches, at least the second one gives something, but not what we are after. Well, it gives, for example, something on L2. So on L2, if p is equal to 2, then the square function then estimating the square function is estimating just each terms of the square function, and for this one it will be okay. But apart from p equal to 2, the method of rotation is also not suitable. Okay, so let me now try to describe what are our approaches, and I will try to do it in 3 degrees of difficulty. So first I will consider k equal 1 when there are just two steps in the procedure. Then I will consider k odd when there are 3 steps. And then I will consider k even where there are even 2 more steps, altogether 5 steps. Okay, so first let's speak about the k equal 1 case. So there are 2 main steps, which we labeled as factorization and then the method of rotations. So factorization means that you can factor the Riesz transform, the truncated Riesz transform, which is written here, in terms of the Riesz transform composed with some other operator mt. And this MT is a convolution operator with a radial kernel. Okay, so now I will speak a bit briefly about this factorization. How do we achieve it? Okay, so this factorization is implicitly shown in the work of Matteo Robic, Perez, and Verdera, and they prove what they prove there is that there is, well, what can be read from the proof is that there is such a factorization with MT being a radial Fourier multiplier with some symbol M. Okay, so once we know that it is possible, you can actually deduce what a useful formula for MT, which I will show you on the next slide. Okay, so we know now that this MT exists from previous results, but now we would like to obtain some formula of it, some formula for MT that is useful for our purposes.
No, actually, I missed what is MT basically?
MT is okay. So you will see in a moment what is the explicit formula for it, but it is for the time being is just an operator that makes this formula valid. And this operator turns out to be bounded on
Okay.
LP. So it is some operator, and observe that the only t on the right, the only t is here, not here. So here there is no t, but here there is a t. So in particular, if we want to consider some bounds for r star in terms of r, then all of such bounds are reduced to controlling this maximal function. Because on the right, maybe I'll show you 2 slides at once. So on the right here, the only MT is here. So if, say, we want to say that the R star is controlled by, let's say that the LP norm of R star is controlled by the LP norm of R, then this is essentially equivalent to saying that M star is bounded on LP because of this composition formula. Okay, and if we want a dimension-free bound, then we need to prove a dimension-free bound from this MT. So in a moment, we will see that there is a formula for it in case k equal to 1, which is useful for our purposes. But let me again say that If, for single Riesz transforms, what it means, this factorization is that we can just focus on those kinds of estimates for the operator m star. And we just want the constant C to be independent of the dimension D. So you can forget about the explicit dependence on P, as I mentioned before. Okay, so how do you prove such estimates for M? Well, it has a very useful explicit formula, which can be quite quickly deduced when you use some property of the Riesz transform. So if let's say we want to write what is MT composed with R squared, Rxj squared, Rxj squared. So by definition, this object MT composed with Rxj is this. This is the definition. But on the other hand, if you sum the Rx squares here, then this is minus the identity because of the property of the Riesz transforms. And this means that MT is minus this sum. Because what I'm doing is I'm summing the above formula here, this formula. I'm summing it over J from 1 to D. And I will get MT times minus identity on the left and this sum on the right. So this is another formula this is a formula, an explicit formula in a way that allows you to say what is the MT operator. By the way, there is a little caveat here. So if you would like to do the same for k equal to 1, then it doesn't work so directly. You need to add some extra ingredient, which I will speak about in a minute, or maybe 10 minutes. Okay, so after we have this, what it means, what it means that we can just focus on estimating this object here. But maybe before going into how can one estimate it, to mention some things, I would like to mention a curiosity that has been recently discovered by Liu, Melentievich, and Zhu. Well, what they proved is that the kernel of this MT operator is a non-negative radial function. And this is quite interesting because if you just view it in this way, like I wrote here, this is just a composition of a number of singular integrals, Rx, composed with truncated singular integrals. And then it, for some reason, for a specific computation, it turns out that its kernel is a non-negative radial function, which is moreover inner one. So this will come back in a moment when we speak about the case q equal to 2. Then there will be a similar operator MT, which is even simpler. But this will be in about 10 minutes from now. Okay, so as I mentioned, that it has this kernel, which is radial non-negative function of norm 1. Okay, but now if we have this factorization, then we can already use the method of rotations. And the way we do it is the following. We focus on the estimate for the LP norm of this object. And the factorization we had was this. This is just copying the previous formula. But now what we do, we apply the method of rotations to the Riesz transform RJT here for each RJ. And this will result on omega j's here, the directional Hilbert transforms here, and the square root constant in front. So it means that this sum is just an average of directional Hilbert transforms of another sum of this form, where omega are vectors from the spheres and omega j's are their coordinates. So once you work a little bit with this formula, and you apply Minkowski's inequality, you just realize that this estimate holds that I have here. Okay, and then there are like the second part here requires some steps, so it's not completely obvious. But after a number of Hölder and reverse Hölder inequalities, which hold on SD-1 for spherical harmonics, you can prove what we wanted. So you can essentially replace what we have here by the square function of f. So the crucial thing that allows you to do it with a constant that does not depend on d is the fact that the object h omega star, the maximal truncated directional Hilbert transform, is one-dimensional. So it is a bit of a complicated object, but it is one-dimensional. It acts and its norm does not depend on the direction omega. So this is the point. So it's you can yes.
So this is where you are using k equal to 1 case, because you started with k equal to 1. So I'm trying to understand
I'm not using k equal to 1. I'm proving k equal to 1 now. So all of it pertains to k equal to 1. But now this object. So in this dimension-free business, what one does usually is that you want to reduce things to one-dimensional or two-dimensional or fixed-dimensional objects. And the one-dimensional objects that I reduce it to is this one, the maximal truncated Hilbert transform. So it's not really one-dimensional, but it's an estimate for its norm. The LP norm does not depend on the direction. So if we want to say, because I'm saying that I reduce everything to here, so the LP norm is here, right? But it's an LP norm of H omega star, which means I can just cross it out because it does not depend on the direction. So it's an LP norm of this thing, and then there is a number of tricks that allows you to come back to what we are really interested about, because we are interested about what is here. Right, but yeah, so this is in the paper how the steps are made, but of course during the talk there is no time to mention it. But the crux of the matter is that we reduce it to an object that has a dimension-free estimate for its norm, and this is a directional Hilbert transform for which the norm LP norm does not depend on the direction. So the norm is here, and now afterwards we are integrating over the omega, but it doesn't matter because then omega already disappears here. So then we will just have we will be left with this object only, and with this, as I mentioned, a number of Helder's inequalities and reverse Helder's allows you to 2 or 3 allows you to come back to the square function. And by the way, this is also the way that the constant is eaten, because here I have this troublesome constant square root of d, but this will disappear after these steps because of the fact that if you integrate over the normalized probability measure on the sphere this function, then this is 1 over d. So it will some expression of this kind will appear, get to the power 1/2, and will eat this constant here. So in the end, it will disappear after these steps. Okay, so now I will try to go to the. Okay, so just to recall, we ended up here with this Rj here, the sum of squares here. But of course, by the classical result of Stein, you can estimate this by just the LP norm of f. Right, so we prove what we wanted, because I was saying that we would like to prove that the m star of f is smaller than f, and this is what we achieved. M star of f is smaller than f here again. And we are done for the k equal 1 case. Okay, but now let's move to the higher order case. By the way, I mentioned also as a result some vectorial estimate, an estimate for the square function. So the proof is similar. It's more complicated because we need to add some extra Khinchin inequalities here and there, but in spirit it is quite similar. Okay, so now let's move to the case k greater than 1 and odd. So there will be one extra step that was not needed when k was equal to 1, but will be needed when k is odd but not equal to 1. So we still have the steps as before, factorization. It follows similarly as before, only that now this empty operator depends on k. So for each k there is a different empty k operator, but it's known that it exists. There is a method of rotations at the very end, but there is one step in between which we called averaging, and let me describe to you what this averaging means and why is it needed. Okay, so why is it needed? Let's say k equals 3. Then one can express the identity operator in terms of compositions of squares of Riesz transforms. So remember that for this expression of MT, it was crucial, the one when k was equal to 1. What was crucial was that if you compose the Riesz transforms, first order Riesz transforms, you compose them like this, then this turns out to be minus identity. Say j equal 1 to d. So if you compose such kinds of Riesz transforms, like you apply this but 3 times, you will get a sum like this. And these objects here are compositions of Riesz transforms, but are not higher order Riesz transforms according to our definitions for some xi, xj, and xl. And what I mean by that is that, for example, if you take x1, x1, and x1 in the formula above, which is allowed because this formula has all the xi's, xj's, and xl's without any restriction, then what we will have as a corresponding polynomial is x1 cubed, but x1 cubed is of course not harmonic. So it's not in the H3 space, and it cannot be, for example, factored in terms of the operator MT. So this is also related to what I mentioned here, that this factorization formula only works when the corresponding polynomial here, which in this case would be xi, xj, xl, this factorization only works when this polynomial is harmonic. And in particular, this would be the case if I, j, and l are pairwise distinct. But in the formula above, we did not have the restriction that they are pairwise distinct. So this is not allowed there. Okay, but there is a way to overcome it. And we call this way averaging. Well, actually, for k odd, there are two ways. So one of them was later realized in the PhD thesis of Maciej, but for the purpose of this talk, I will mention about just one way, and the pro of that is that this way also works for even case, whereas for even k, the other way maybe does not work. So how to remedy this problem? Okay, what the remedy is to average over the special orthogonal group. So for this purpose, what we do, we denote by I the set of all indices in 1D cubed, which are pairwise distinct. So it cannot be that they are the same. And then it turns out that the identity is a restricted sum of squares of Riesz transforms of this type when the sum is restricted to distinct indices. So why this might be helpful? Well, I told you that we couldn't just put, it was true that identity is the sum of j equal to 1 to d Rx n1 xn 2, sorry, n in 1 to d, n in 1 d cubed, Rx1, xn2, xn3 squared. This formula is true, but for all such indices, it is not allowed to use the factorization method. So we need to focus on the indices which are pairwise distinct, like here, and then we are allowed to use the factorization. But the problem was that this sum just by itself does not recover the identity. Only after it's averaged over the special orthogonal group, it does recover the identity. So this is why we need to add the step which we called averaging. And this U is some conjugation operators. The important thing is that this operator is bounded on LP. Okay. So once we have this averaging, this procedure in effect reduces our task to controlling the this operator which are written here, RT. And the reason is that this is sort of a replacement for what we had. This is a replacement for the formula in empty. So this operator would appear in the formula here. Sorry, maybe I try to do it slower. Okay, so this operator would appear if we sum this formula here with functions with the truncated Riesz transforms in front, like before. So it will appear here, and essentially our task will be reduced to controlling this object. Okay, and just note that when k was equal to 1, then we wouldn't have products of 3 terms, but of just one term, and it will be just say Rx nt Rxn, and this sum was exactly our minus mt1 operator. In this case, it is not exactly, but because of this formula above, the one that I had here, it reduces to controlling just this object RT. So this formula for the identity allows one to just focus on this operator RT, instead of the initial operator MT. Okay, so we just focus on the RT operator, and then the proof is essentially similar to what we have before, but we just need to make the steps for the RT operator, not the MT operator. So in this case, when k is odd but not equal to 1, we are focusing on RT, not on MT, but it's enough to estimate the RT operator, and its structure is similar to the one that we had for k equal to 1. So therefore, the method of rotation works for it, if you work a little bit with it. Okay, and there is one more case which I would like to describe. So we treated so far k equal to 1, k greater than 1 but odd, and now we are moving to k greater than 1 but even. Okay, so in this case, there are even two more steps. So let me first underline which are essentially the same as before. So the factorization is as before. The averaging is also as before. Okay, the method of rotations, there is a word method of rotations here, but it's not the real method of rotations, but the complex method of rotations. And there are two other steps, which we call extension to CD and then restriction back to RD. Okay, so what do I mean by that? The problem here with the k even case, the main problem is that the real method of rotations requires that the kernel kpt of Kp is odd. And when we consider K even, the kernel of Kpt is not odd, but it's even. So we cannot just apply the method of rotations in this setting. And for this reason, we need to devise some other strategy. One little curiosity here of similar type than what we had for K equal to 1 is that when K is equal to 2, then it turns out that the transition operator M2T is exactly equal to the Hardy-Littlewood centered averaging operator. So I was quite surprised to see it the first time. So what it really says is, for example, that if you take Rx1, say x2t, the composition of Riesz transforms, truncated Riesz transform corresponding to the polynomial x1, x2, then actually this is the Hardy-Littlewood averaging operator composed with just the Riesz transform. So it says that the truncated Riesz transform is a composition of the Riesz transform with the Hardy-Littlewood averaging operator. So this means also that the case K equal 2 is easy because all the estimates in this case that we are interested in can be deduced from estimates for the Hardy-Littlewood averaging operator, and these estimates are well known to be dimension-free. This is another result of Stein from the 80s, even for the vector value setting. Okay, so as I mentioned, these are the reasons that the steps are needed. But now let me go to describe the extra ingredients for K even. So what do I mean by extension to CD? Well, the idea is that you replace the kernel Kpt, the two kernels, Kpt and Kp. These kernels are kernels on Rd, and I would like to replace them with appropriate complexifications, which we denote by tilde, Kp tilde t and Kp tilde. And these complexifications should be functions on CD, not on R2D. Well, the reason for doing it is that when we go to CD, then there is a method of rotations which works for all functions, not only for even or odd functions, but for all functions. So for example, what does this Kp tilde mean? Well, it's quite simple. What you just do, you take the previous kernel and you put this P here above is a polynomial. So you can write it, you can write an argument x plus iy for this polynomial, and this means just, of course, x1 plus iy1, x2 plus iy2, etc. Okay, and in the denominator you just take the complex absolute value of the vector of the number x plus of the vector x plus iy. The constants change a little bit, but for the purpose of this talk, we don't need to care. We don't need to remember what those constants are. Okay, so once we have done this extension to CD, the next step would be to use the complex method of rotations. And this complex method of rotations is a tool devised by Ibanez and Martin in a 1995 around this time paper. And this, what it means is that we will be interested in this operator RPT star, because remember that when K was equal to 1 or K was odd, what we are doing, we are expressing this RPT in terms of some integral over some Hilbert transforms. So we would like to do the same here now, but now our kernel lives on the space CD, which we sometimes identify with R2D. But it turns out that there is a formula which works for any kernels in CD, not only for kernels which are odd. And the formula is the following. You take d to the power k over 2. So again, this would be eaten by the estimates in the process. And now you have a polynomial, the one that corresponds to your considered Riesz transform here of omega plus I sigma. And what you have else, you have not the Hilbert transform, but some other object, which I will describe in one page. This object is called the kth power of the truncated complex Hilbert transform. But let me just say that the d sigma here is the spherical measure on S2d minus 1 normalized, and sigma in this notation will be omega plus I sigma. Sorry, zeta will be omega plus I sigma. Okay, and what is this H zeta t k? Well, it's given on the next slide. So this is an object called the kth power of the complex Hilbert transform truncated at t greater than 0. So if not for this truncation, it would be an object with this kernel. So the kernel is essentially 1 over lambda squared. Well, let's say k is equal to 1. So it would be 1 over lambda squared times lambda over the length of lambda, which in this case would be just, let me write it here maybe. k is equal to 1, it would be lambda over lambda cubed, say. But now this is not a one-dimensional object. This is a two-dimensional object because the domain of integration is C. But that's still okay for our purpose because we would like to have a dimension-free estimate. So when we have an object that just depends on two coordinates, that's still okay, as long as its LP norm will not depend on the direction zeta here. It can depend on k because we are allowed to have dependence on k, but we are just interested that the LP norm of this operator or the maximal function corresponding to it does not depend on zeta, and this is indeed the case. So this is why this object is still useful to us, and the rationale for going to CD was to use this formula for H, was to use this formula above, the one here. And in this formula, I mean this formula. When we wanted the rationale for going to CD was to use this formula, and in this formula the object H zeta k t appears. So this is why we need to have estimates for its LP norm. Okay, so this was step 4, but there was also step 5, which I also mentioned. And the step 5 was that we need to restrict back to RD. So, okay, we now proved some result when we follow those steps. We proved some result for the LP norm of the complexified Riesz transform on C to D. Sorry, on CD, which is essentially R to D. But now we would like to go back to our initial question. So we are not interested about complexified kernels K, P, T tilde, but we would like to go back to our initial kernel K, P, T. There is a way to do it. And for these kinds of kernels, the easiest description of this way is just the integration of this kernel in the variable y in RD. Then it turns out you'll get back to the kernel, to some kernel, the integrated kernel of this. So what we are doing, you are integrating kpt tilde of x plus iy dy over RD. And what you will end up is some kernel, which I denoted by script kpt of x. But there is a problem with this kernel, which I pointed in red here. The problem is that this is not the kernel that we started with. So we will reach some kernels, calligraphic kpt of x, but this will not be the kernel that we started with. So there is still one more step to perform to finish this argument. And this step is that we need to estimate the difference of the two kernels, but fortunately this can be done. And we not only need to estimate the difference between those two kernels, but we need to do it in a dimension-free way. But for some lucky chain of events, this can be done, and we can just go back to our kernel kpt. Okay, so this is just a rough description of the 5 steps that we had, and in the remaining several minutes, I would like to mention possible generalizations that maybe there is a way to generalize those results. Okay, so what about general singular integrals? So I was speaking about singular integrals which were of the form Rp f of x, say integral over p of, now I write it in a slightly different way than previously, but it's equivalent. Y to the power d plus 1 f of x minus y dy. So all of these integrals that I was mentioning before were of this form. So what I did, I just put y over the modulus of y in the value of p, but p was, in each of the cases, p was a polynomial which was homogeneous of degree k, so I'm allowed to do it. So more general kernels of this type would be, you just have a function omega on the sphere. You integrate omega of y over the length of y with respect to this weight. You make a singular integral out of it. Then you make a maximal singular integral, which means just you truncate it at the level x minus y greater than t, and take the supremum over t greater than 0. And you would like to ask a similar question. If, say, the initial, the maximal function corresponding to these types of operators is controlled in some way by the operator itself. Okay, so it turns out that even such an L2 estimate with any constant, not even thinking about whether it's dimension dependent or not, this may hold only if omega satisfies a certain algebraic condition, which is related to its expansion in spherical harmonics. And this was sort of the most important part of this series of papers of Mateo Robic, Perez, and Verdera. So they established a condition under which this is possible, and if the omega function does not satisfy this condition, then this is impossible. So for sure, we know that this is not always possible. but it's not clear if the method that we have can be generalized to other setting when it is possible. So it is possible when P is just when omega is a harmonic polynomial, which is homogeneous of degree k, meaning a spherical harmonic. But if it's not of this type, then it's not clear if such a result is possible or not. So we tried a little bit, but we don't know yet if there is a way to generalize it past the Riesz transform. So one also thing that we don't know is how is the dependence on k involved in those estimates, because as I mentioned, the upfront factor C of k, we didn't care about the dependence in k, but who knows for that, what this estimate exactly should be. Okay, I think this is all that I have prepared. So thank you very much for your attention.
Thank you, Wrobel, for a very nice talk. Okay, so are there some questions from the audience?
So, in your presentation, when you thank you for the elaborative talk. So when you mentioned the recent result by some people, we can write MT as a phi t star f.
Right. So I can go back to the slide. So give me a second.
Yeah.
Right, from a year ago. Where that was. Okay, here, right.
Yeah, so you mentioned this when you were discussing for k equal to 1 case. My question is, so this result is true for all k, right? Not just particular k equal to 1 case.
So there is an operator MT that is bounded, is true for all k, but what is the formula for phi t? And whether it's non-negative or not, this is not so clear. I think we have some sort of initial results that suggest that we can write it in some terms of formula, and it won't always be non-negative. And for example, it won't be probably that its L1 norm is always 1. So this is like we have some hints on that, but it's not known if you can say something about this MT apart from the cases k equal to 1, which is here, and k equal to 2, which is the Hardy-Littlewood maximal operator. So in the two first cases, the kernel was positive, but I think this I have the impression that it might not continue for larger values of k. So it's not so clear what this case. And also, if you have asked about this, one other funny thing here is that this kernel, as I wrote here, but maybe not mentioned, is a kernel that is increasing for x smaller than t. Then it explodes at x equal to t, and then it decreases. But it does it in a way that it's still in L1. So it's not a decreasing radial kernel or whatever. It is actually increasing to some part, and then it only decreases. Plus, it has a singularity when x equals t. So the Hardy-Littlewood maximal function corresponds to the kernel phi t. Here it would be just the kernel 1 over the measure of the ball, characteristic function of the ball. And this kernel is of a different sort, that it's constant, then it's 0 after some time, right? But this kernel is yet different, that it's growing to infinity, then it explodes when x equals t, and then it decreases.
Okay. Okay, so my last question is that so when you are writing MT as a multiplier operator, is there any specific nice property of this multiplier, like it satisfies some kind of Hermann-Millin or
okay? So the reason I mentioned this is that because in the previous paper when we had with Maciej on k equal 1, so we had k equal 1. Maybe let me go to the slide with the multiplier. So give me a second. Multiplier was, yeah, okay. So the reason I mentioned this is that in the proof that we had with Maciej for p equal 2 and k equal to 1, we used the properties of the multiplier. So this multiplier had some specific estimates which allowed you to prove the L2 result. But then it was not so explicit. It was some integral of some, I don't remember exactly the formula, but it was some integral of Bessel functions, which what Melentejewicz, Zhu and Liu did. They expressed this integral in terms of something more explicit, and this allowed them to prove the result. But when we are working on the p equal 2 case and k equal 1 with Maciej, we did not know that this integral has any other expression, so we just worked with some estimates for Bessel functions. Okay. So I don't remember the exact formula, but it was some integral of some Bessel functions, J nu of some argument, and then it was truncated here. So it was looked to as a complicated formula that had no expression, no more explicit expression, but it turned out that it was not the case. But it satisfies some nice estimates, I believe. Right. So what I remember, for example, now is that you can prove, let's say t equal 1. This is direction invariant. So you can prove something like this for m. That m of psi minus 1 is smaller than psi over the square root of d. Okay. That m of psi decays. 1 over, no, so it's never 1, it's something, right? Psi over the square root of d, and then estimate for the derivative. And if you have those three, then there is a general machinery that allows you to prove at least L2 estimates.
Okay. Thanks for that. So I will end with this. So is there any analog of this kind of problem to groups, like for example Heisenberg group? Because I believe.
Okay, I don't know, but I think this has not been investigated on groups, even on the Heisenberg group, because already if I'm not mistaken, already the result of Perez and his co-authors, of Verdera, Perez, Orobicht, and Mateu, this already has not been generalized to groups. So this is the first step, because their result depends on, they don't care about the dimensional dependence, but already this is not generalized to groups. So first step would be to generalize this to groups and then to try to make it dimension free, but this we don't know. This is also not generalized to, as far as I know, to non-convolution operators. So even on, say, we are staying on RD, but we would like to compare the truncated maximal singular integral, but with a non-convolution kernel to the singular integral, and I think this is also not known as far as I know.
But you are not using exactly. I may have, when k equal to 1, you mentioning it can be written as a convolution operator. But when you're writing this k greater than equal to k greater than 1, odd or even, are you using convolution structure specifically? Because I remember you are writing relation with MT and RT.
Okay, so as long as I could factor something that does not depend on t outside, so the way it's done is that you can factor some MT outside, and then you have some other operator that does not depend on t inside. So as long as I can factor something depending on t outside and something that I know inside, it should work. But it's not clear how to do it if it's not convolution. So there is no prohibition in, like, I don't know, in the method or whatever. But I don't. First of all, I also have not considered it very thoroughly, so I'm not sure. But the way I see it, it might be not so easy. One could try. There is a chance that it will work.
Okay, thank you for a nice elaborative talk.
Are there any other questions from any other audience? Okay, if there are no more questions, let us unmute and thank the speaker for a wonderful talk. Okay.
Thank you very much. Thanks again for the invitation.